So Tracy, ready to learn some physics? I want to take it that you know calculus. Really? So we are brought here today. This is so stupid. Hold on. This is like how I teach like my students. Like, yeah, I don't know. I like switch into like some kind of.
Setting.
Hold on, let me make sure everything. All right. I think that's good. So, tell me if you look in the camera and you can't see like what I'm writing.
Fine.
But I'm just gonna upload it anyway, just because
Okay.
this is for you
Fine.
and me. So we are brought here today to solve a nice problem out of, I don't have the book on me. What was it? Classical Dynamics from Marion. Chapter 2.3. Question. If a projectile is fired from the origin of the coordinate system with a velocity v0 and in a direction making an angle with the horizontal, okay? Calculate the time acquired for the projectile to cross a line passing through the origin and making an angle beta. Beta is a Greek letter. Less than alpha. So just like 1 is less than 2. Okay? That's all that is. Making an angle beta less than alpha with the origin. Alright, so what's this saying? So, if I take this marker, okay, and I toss it over there, alright, so I take another one. So, we can probably find out the time it took for it to get over there by measuring the distance. But if I wanted to measure the time when it's like at that point, when it's falling down, I want to take that kind of time. That's what this is asking. So, first, let's draw our picture. Our y-axis, our x-axis. And we have a projectile. It is launched from my hand. Like this, okay? Like, launched. That's what I mean. It's launched with some velocity. Velocity meaning distance over time. Like, I take 3 steps in 1 second. 3 steps per second of velocity. That's all that is. So this marker is being tossed at a certain velocity. Alright? So this is our x. So we're given it's thrown at an angle alpha. This would be thrown differently if I change the angle. So like if I do it like this, or that, if I do it like that, or throw it like this, it has different trajectories. Would you agree? Just like a basketball. You throw it up, you throw it straight, you throw it at an angle like that. Yeah, exactly. The angle matters, all right? So, I'm running out of markers to throw, but we're throwing it. What kind of shape does it make? Like a curve, right? That's called a parabola. And that's what a projectile does. It makes this arc curved path. You throw it up, it reaches a maximum height point, and then it goes down. Okay? So, what is this asking? If a projectile is fired from the origin of the coordinate system with the velocity v0 and in a direction making an angle with the horizontal, this x-axis, that's what we mean by horizontal. Alright, that's our horizontal. That's the floor. Calculate the time required for the projectile to cross a line passing through the origin. So the origin, right here. That's all that is. Where x and y meet are the same, 0. So we make another line. Pretend that's straight, okay? For demonstration purposes, okay. So pretend this point right here. Now this line, it has a different angle than this one. So let's call that beta. So that's different. That angle is different. If this was alpha, this is alpha, and then this purple one coming out, this one beta. This one has a smaller angle. Yeah. This is a smaller angle, right? All right, so that's what beta is. So this is a line starting from the origin, passing into the curve, okay? Let's conserve these markers so I can throw more. So, pretend this is a straight line. All right, now, we know some trigonometry. Draw a line down, horizontal. This is our slope. We can now, so let's see, it comes over here at some point, so we want to find a time for this. So let's call that t. T naught. It's just some random time on here. I could have called this t naught, but we're just trying to find what the time is at this point. Okay? It's just a time value. All right, I think we're almost done setting it up. Let's see. Calculate the time required for the projectile across the line. Okay. Everything's set up. Well, let's see. Let's call this a distance. X naught. X naught, well, you'll see why I'm saying X naught. X naught, the naught just means 0. Like, it's just a name for it, okay? So this is just a distance from here to here, okay? Now, we look at the horizontal. If you remember, like, triangles, you know that we can find a cosine of this angle according to its hypotenuse. So this distance, from here to here, to this point, we call that cosine beta times x naught. Now, I don't know if you remember sine, but sine has a factor in this too. So, this distance from, well, okay, yeah, from here to here, I just did this just to show that from this point to this point, is x naught sine beta. Because this distance is with respect to this angle beta. All right? So we have located this point. So let's call these coordinates. So you remember like x, y coordinates on a grid? So that's going to be our x coordinate, x naught cosine beta, x naught sine beta. They're just numbers, really, for determining this point. Okay. Let's assume you know calculus, just for, why not? It's really easy. So, we talked about velocity, right? You know what velocity is, like 3 steps per time, you know? Okay, now, what if your velocity changes? So instead of 3 feet per second, what if I start increasing it to like 5 feet per second, okay? We call that a change in velocity. All right, and that change in velocity with respect to a change of time, that's an acceleration. That's like, you know, when you accelerate in the car, yeah. So let's start from there. Acceleration, A is equal to, just follow me here. This D, let's just call that, you know, like a change, you know, you're changing, okay? You don't really need to know too much about this. Yeah, this is just for the viewers. Kind of know. Just wait, we'll come back to you. All right, so if you know some calculus, then let's say A is equal to dV dt, okay? All right, so A dt is equal to dV. We integrate both sides. Let's see, from 0 to t, 0 to v. Let's see, so A t is equal, let's say v naught. Yeah, that's Okay. So let's see. We have v is equal to v naught plus at. Trace, look, man, look, we have an equation now, all right? What's this say? A velocity. We can call it our final velocity, you know. So this one right here, the v naught, we call that our initial velocity. So, you know, if I was walking 3 feet per second, and then I started increasing to 5 feet per second, that 3 feet per second will correspond to the v naught, and the 5 feet per second will correspond to the v. All right, makes sense, right? This a. That's our acceleration. That's when, you know, the change, and, you know, from 3 feet to 5 feet. That change when it's from 3 feet to 5 feet, it's our acceleration. Our time. That's just our time that we did throughout the entire duration. When we multiply time by acceleration, we get a unit, we get a velocity. So velocity plus velocity is equal to velocity. Math checks out, okay? That's like saying you can't add mass and, you know, time. You know, it just doesn't make sense, right? All right. So, this is not so helpful yet, because we want this in terms of a distance. All right, so what's a velocity, you may ask? You're right, it's just a distance over time. So, what do we do with such thing? All right, so let's redefine v. V is dx over dt. All right, let's take that. V dt equals dx. Let's integrate both sides. Why not? 0 to t, x naught to x. Okay. That equals v times t. X naught. X minus x naught. Okay. So, if we wrote back, so if this is what we have for v, we're just redefining. I could have just wrote these equations, but I wanted to show you where they came from, so I'm just not pulling them from thin air. Okay. So if vt, let's pull this up here. If vt is equal to x minus x naught, we're gonna call this. Okay. So what's our v? We already have v down here, right? V naught plus at. So let's just plug it into there. You agree with me? That's what v equals. I plugged it in. I'm not doing any tricks. T multiplied by v naught. V naught times t plus a t times t. That's at squared. All right. Ooh, wait, I did something wrong here. Oh, we'll address that soon. Okay. So down here somewhere, I'm missing a factor of 1/2, but that's okay. It's just a number, but that's okay. We'll find out what's wrong with that later. So this video is already kind of scuffed, but that's okay. And that's our equation that we're going to start using. Okay? So let me erase a bunch of this. Let's see. I could have just... I'll find the issue later. Just erase this. Rewrite this. We're solving this problem from first principles. Just for today. Only today only. So, let's rename this delta x xt. Because when we throw the position is going to be changing over time. Alright, so, you know, from the position here, the position is x. In about 3 seconds, it's going to be up here. So, with some time, the position is going to change, okay? So we call that a function of t. Cool, cool, cool. Okay, so now I think we got what we want from this. All right. So this x, this is in terms of x, but we can really simply redo this in the y direction. Okay. So this is in the x direction. Let's rename our velocities with a little x, like v naught x. Okay, sure. Let's do that to our acceleration too, because there can be an acceleration in the x direction and the y direction. All right. So if I throw this cloth, I don't want to throw the cloth. If I throw this marker, its acceleration may be changing in the x direction, but in the y direction, it's not changing so much. Okay. That could be in reverse as well. So let's rewrite this as y. So let's rewrite in the y direction. Yt is equal to initial velocity yt plus 1/2 ayt squared. Okay, cool. So for our projectile motion problem, if you're a student of physics, there's no, in projectile motion, there's no acceleration in the x direction. So if there's none of that, then we can call this term, damn, I don't know what part it got on me, but that goes away, that's 0. Now, there's this thing called gravity. It's really cool. That rate at which it falls at a constant rate every time, no matter what point you take it from. We call that g. So this acceleration in the y direction is negative g. Why negative, you may ask? Because if we have our coordinate system, if this is positive y, that's negative y. So when you go up, you go down, call it negative y. If this is, wanting to go down, then we call that negative g, okay? Because it's coming back towards the Earth, as opposed to opposing it, going up. So let's rewrite this. Y of t is equal to v naught yt minus 1/2 gt squared. All right. So there are these nice definitions. V of x, initial velocity in the x direction. Remember this cosine x with respect to this hypotenuse. So, initial velocity, it's a vector. All right, and we're going to represent its x component as initial velocity in the x direction as initial velocity times its cosine of its angle. This initial velocity has an angle, alpha. We're just getting started. I know you're excited. This is what I do all day. So, there's that for the y direction too. Alright? So we're going to take these two values and plug them in. Alright? We're getting to the fun part. So, let's erase these, and let's rewrite them. I hope everybody wrote them down because I don't have much room to work with. Xt equals v naught cosine alpha t plus 0. But we don't need to write 0, right, Trace? No. It means nothing to us, right? Yeah. The distance in the y direction. That's on camera from here. What now? Right. Initial velocity sine alpha t minus 1/2 g t squared. Alright, so this is for any time. If we knew a time at any moment where this thing was, we could plug in that time right here and get exactly, what point it would be at. That's pretty powerful, right? I could throw that marker. If I knew the time, if I took a picture of when I did that, I could find the distance I traveled. That's pretty powerful, right? So, if we want to find some time t naught, this is where our setup comes into play. Can you see that on the camera?
Yep.
All right. So what we want to find the time at this position. How do we know like where that position is? You're right from earlier. We defined its coordinates. All right. So let's rename this T naught. All right. So I'm just plugging in T naught right here. So I'm just adding a little subscript. Okay. Let's do that to all T's. All right. Okay. Okay. Now, what is this V naught cosine alpha? Let's see. Let's see. This x T naught is equal to some distance, right? That's our knot. So, if that's our distance right here, of this point, we can re-express this as initial velocity cosine alpha T naught. Now we're going to do it for the y direction. Oh, well, it'll be that one. X naught sine beta is equal to V naught sine alpha T naught minus G T squared naught. Okay, cool. Just erasing this because we don't have much room. And the camera is kind of bright, or the light's kind of bright. It's reflecting off into the camera. That's a mess over there. So, we want to separate T naught from all this. Okay? How can we do that? Sure, let's combine the equations. How? Well, everything kind of looks the same. So on this side, if we multiply each side by sine beta, and then on this equation, so let's call this equation 1, equation 2. We multiply both sides by sine beta, and then down here, so it's sine beta over here. We multiply both sides by cosine beta. Let's pretend like, I can multiply from right here, right? If I had room. Okay, I didn't break it in half, right? Multiply both sides by the same thing. All right, look at this sign. There's a sine beta, cosine beta, x naught. There's a sine beta, cosine beta, x naught. They're the same thing. So we tack on a negative to both sides. And then we add both equations. What would happen? If this is the same, this is the same, but this is a minus. What is it? It's 0, yeah. So, we take this down, erase this for spacious completion. 0 equals negative V naught cosine alpha. This video is too damn long, but this is what happens when I'm given a victim to teach. I like to do my little shenanigan. Okay, so cosine plus V naught sine alpha. I'll rewrite this. Cosine beta T naught minus 1/2 G T squared naught cosine beta. Let's rewrite this now. All right, let's start from the top trace. 0 is equal to negative V naught cosine alpha sine beta T naught plus V naught sine alpha cosine beta T naught minus 1/2 cosine beta T squared, let's write G, G T squared naught. So trace. We gotta solve for T naught, man. And I don't think I know how to do this. So we have a T naught here, we have a T naught here, we have a T naught here squared. There's a 0 here. So what can we do? 0. 0 divided by anything except for 0 is 0. Alright, so can I divide both sides by T? T naught? Yeah, cool. So if I do that, this over here, 0 divided by T naught, just so 0. So then this goes away, this goes away. And trace, look, this squared, T naught squared divided by T naught. It's just T naught. So look, we only have one term, that's T naught, and we have a 0 on the other side. So let's move this over here. Rewrite. So, we're really close to finding out what T naught is. So, this is just all, multiplication. So if we want to undo a bunch of this to find T naught, what's the reverse of multiplication?
Division.
Division, yeah, dude. So, let's multiply both sides by 2. So, let's see. Equal 2. We're going to do a giant bracket. Same thing as the parentheses, pretty much. I think we're almost there. I'm going to cringe if anyone that I know sees this video. I'll probably end up showing them. Alright, so we multiplied by both sides by 2. That's gone. We want to get rid of this G. What do we do? I don't know. Divide by G. Yeah. Alright, we have a cosine beta. What do we want to do? Divide by cosine beta. It's that easy. So all that equals T naught. So we can do better. We can simplify this. So let's take a knee. Take a knee always ended well. 2 G. Hey, look. There's a V naught in each of these. Let's factor it out. Let's take it outside. All right. So we're going on the inside. So cosine beta. So sine beta divided by cosine beta. What's that? That's that tangent, that we learned once upon a time. So let's see. So we still have a cosine alpha. So since they're different angles, we can't just, do the same kind of tricks. So that's a cosine alpha. I think this is how I ripped my pants the other time. So let's stand up. There's a minus here. Alright. That V naught is outside. Alright. Cosine beta. Ooh, trace, look. Cosine beta divided by cosine beta. What's that?
0.
It's the same thing. It's like,
T naught. It goes on by.
what's something divided by the same thing?
Just
Like-
the same thing. 0.
Is it? What's 4 divided by?
1.
Yeah. No worries. So let's see. So that cancels out. So this becomes 1, right? Alright. So then we're just left with this sine alpha plus sine alpha. Alright, let's rewrite this. So we did all this math. We built all this up for the most part. Except for that hiccup earlier. I don't know where I missed that 1/2. So this time at this point that intersects the origin with a beta less than alpha is T naught equals 2 V naught divided by G. We're gonna rewrite the positive first. Where's this cosine beta came from? Sine alpha minus cosine alpha tangent beta. All right, let's see if that's good. Is that the same thing in the bracket?
The circle.
Yeah. Same thing within the square?
Yeah.
Cool. All right, well, that's it. That's all I really wanted to do today. That took really long, so yeah. Let's do another one sometime. Let's take a look at all the poor markers that were lost in the process of this. I still have plenty more. All right. Whenever anyone can see that.